So let's put a little bit more details behind these marginal social cost that we mentioned. Remember that if somebody is just producing electricity, burning coal, and people are just buying, then you end up with some optimal quantity of electricity and price of electricity, which may be all hunky-dory, but then you are emitting carbon dioxide, particulate matter, and so on into the air, and you are digging up coal or importing it and creating other externalities, as we call them, which is the marginal social cost. So this is now to be related much more specifically to the social cost of carbon. So there is a background level, as we said, let's say pre-industrial level of 280 ppm or so, 300 ppm or so. Then each additional ton of CO2 put in is going to create these kind of externalities, which is the additional social cost of additional carbon. So how is it calculated? Obviously, it's a very complicated business. Sounds theoretically nice, like ecosystem services and value of nature, but non-market goods always create issues. So estimates of the social cost carbon are calculated in 4 steps using specialized computer models, which means they are based on many assumptions, especially about the future, because often social cost of carbon is where we are headed and how to charge tax or carbon tax or other regulations, market-based regulations, to drive the external cost to be included into the price that is either passed on to the consumer or is subsidized somehow by the government and so on. So in step 1, you predict future emissions based on population, economic growth, and other factors. Step 2, model future climate responses are needed, such as temperature increase and sea level rise, because they determine also what the future cost of emitting carbon is going to be. Assess the economic impact that these climatic changes will have on agriculture, health, energy use, and other aspects of economy. So you are taking somehow temperature, precipitation change, sea level rise, population changes, and so on, and converting them into economic impacts. So there is a lot of details there, including things like damage function, which is kind of a fuzzy number of how much damage would be caused by a cyclone in this economy versus that economy. Cost of life, for example, in a developing country hit by cyclone, India, Bangladesh, let's say, versus hurricane killing somebody in the US. They're going to be very different, right? For example. Step 4, convert future damages into their present day value and add them up to determine total damages. So this is where something called discount rate is involved, how to estimate future damage in their present day value. So discount rate is something you probably have been exposed to somewhere else. Basically, if somebody says I can give you 90 cents today or $1 later in a year, or 90 paisa now and 1 rupee in a year, you would probably be happy to take 90 paisa now instead of waiting for 1 rupee in the future, because you discount the money with time. The value of money you can have now is less and less for you, because you can take the money now, you can invest, you can do all sorts of things with it. So I will leave it there, but you can read much more about the discount rate. And of course, the key question is, what is a good assumption of a discount rate? Is it 10%? Is it 3%? Because if you assume 10%, the investment you make today to protect the future becomes devalued very quickly. Whereas if you assume the discount rate is 3%, the value of investment you are making to protect the future is going to be much higher in 100 years or whatever. So it's the idea of how you discount the future. These 4 steps are completed to obtain a baseline value for the damages of emissions. Then the modeling process is repeated with a small additional amount of emissions to see how much it changes the total cost of damages. The increase in damages from from additional emissions provides an estimate of the social cost of carbon. So it's the additional ton that we're always worried about. Model is then run hundreds of thousands of times to evaluate the uncertainty in the estimates. So in this example here, the schematic from the resources for the future, social cost of carbon has been calculated to be $50 per ton of CO2. So in the baseline scenario, there is $50 per ton, and in policy A, you are taking $50 per ton, and there is an emission of half a billion tons of CO2. So increase in emission due to policy A is going to cost you 25 million. So cost of policy A due to added emissions is $25 million. In policy B, you are decreasing the emissions by 500 million tons. So again, 500,000 tons. Why am I being so thick? 500,000 tons at $50 per ton. So there's a decrease is going to cause a benefit of $25 million because of policy B and the related decrease in emissions. So in the real model simulations, you take number of trials, a number of simulations that the model makes for different discount rates. This is for actually the US government's estimate of social cost of carbon. So average global social cost is estimated to be here at $75 per ton. But for three different discount rates of 7%, 5%, and 3%, you can see that the uncertainty of the social cost of carbon per ton, dollar per ton of CO2, is very different. So with $5 per ton, you are here, obviously the social cost ends up being very low and the uncertainty ends up being very low. When you up it to $14 per ton and a combination of discount rates of let's say 5%, 3% or 7%, you're going to end up with uncertainty range here, and if you assume 2.5%, then you end up with a range of social cost of carbon that is very large, going even from negative here to as high as $200 per ton. I mean, this is a model, it has a lot of assumptions about the future, as we said, about technologies, population, policies, impacts, damages, etc. So I just want to tell you that such estimates are made, and it's a serious business. So here you are looking at global social cost of carbon in dollars per ton of CO2, and the US domestic social cost of carbon. With 2.5%, the global estimate comes out at 75. Obviously because of the differences in damages and so on. For the US, it's assumed at $10 per ton of CO2 from the model, 3% 50 to 7, 5% 14 to 2, and at 7% it's 5 to 1. So the higher the discount rate, the lower the social cost of carbon, both for the US and for the globe. Basically, you are discounting the future and saying the social cost of carbon is not very high, because any investment we make is going to lose value very quickly. People do nonetheless detailed calculations here also for, I think there is an RCP calculation coming up next. So damage function specification, as I said, adds a lot of uncertainty because it's very empirical as well. And here are the shared social socioeconomic pathways and representative concentration pathways, and cost of social country-wise social cost of carbon, the median values being shown here. So you can see that poorer countries or developing countries have a large range under some scenarios. USA here, so these are the scenarios, these are the color codes, and China is here with this range, and Russia, Canada, DU, and Great Britain and Sweden are all here. So this is the map of the country-wise social cost of carbon, and as you can imagine, the developing countries or global south in general have higher social cost of carbon because of the impacts one can expect and the population and the combination of things that we talked about. Looking at the various dependence on RCPs and shared socioeconomic pathways, depending on whether you aim for sustainability, middle of the road, regional rivalry, inequality, and fossil fuel development, which is obviously not very friendly, so you get various range of RCPs in each of them, and the social cost of carbon can range very, very widely based on which scenarios we choose for the future. Long story short, just remember that social cost of carbon is real, and this is just the way to think about it, that how we estimate it is going to depend a lot on the kinds of assumptions involved for the future, especially the discount rate on the investments, or how we estimate the cost of carbon per ton. And either way, countries that are paying a price in terms of climate change, for example, if you think of historical responsibilities, North America and Europe have emitted most of it, but now since 1990, China is beginning to dominate. India is picking up. US is in second place, EU in the third place, India in the fourth place. So social cost of carbon is real. We have talked about extremes, impacts, and so on. So how do we assign the blame for events is separate. It's called loss and damage, where a country that experiences, let's say, a cyclone or a typhoon has additional damage done because the cyclone is stronger than it would be in a counterfactual world or where there was no human impact. Then who pays for the additional cost? That's kind of different mechanism than estimating country-wide social cost of carbon and global cost of carbon. And in the end, it all comes down to how things are going to be negotiated. So I will show a little bit about cost of climate change. We have already looked at impact on economies and so on. So economics is kind of a difficult business, but nonetheless we have to worry about it in terms of mitigation, adaptation, and damages. Okay.